This is a sine of something cubic. This is a cubic equation. Pause the video now if you think you can solve it. It seems like high school math focuses on solving equations, and for good reason. Equations describe the relationships about the things that we observe in nature. Here's an example of a linear equation. 5x minus 10 equals 0. Now this equation is both easy to solve as it is to check. Did you get it? It's x equals 2. Here's how you solve it. First, you add 10 to both sides of the equation. That gives us 5x equals 10. Next, you divide both sides by 5, and 10 is evenly divisible by 5, so we get x is equal to 2. Pretty straightforward. If you wanted to check it, we simply substitute 2 into the equation for x. 5 times 2 minus 10 equals 0. And with a little bit of check, it does. So linear equations are pretty easy to solve, and we spend a lot of time in high school algebra learning about them. But what about a quadratic equation? Consider this quadratic equation. X squared minus x minus 1 equals 0. Do you remember how to solve this equation? You might remember something called the quadratic formula. Here it is. So if we use this formula to solve that equation, what do we get? That's right, we get x is equal to 1 plus or minus the square root of 5 all over 2. So this value represents two values actually. 1 plus radical 5 over 2 and 1 minus radical 5 over 2. Both irrational real numbers. Quadratic equations always have two solutions, but sometimes we count one of those solutions twice. And in the event that we say that there are no real solutions, we know that they have two complex numbered solutions. We'll talk a little bit more about that later. For now, let's consider how do we solve a cubic equation. So in order to solve a general cubic equation, we're going to have to go through a few steps. Now here I've taken the liberty of dividing out the cubic equation by the leading coefficient, putting it into monic form. Now we're going to make the substitution x is equal to y minus a over 3. What this is going to do is produce something called the depressed cubic equation. Now all a depressed cubic equation is going to be a cubic equation without its quadratic term. Let's see what this looks like. So after making a substitution of x equals y minus a over 3, we get an equation that is of the form y cubed plus py plus q equals 0, where p and q are real numbers. We can find the values of p and q from our original equation using the following equations. P is equal to b minus a squared over 3, and q is equal to a cubed over 9 minus a cubed over 27 minus a times b over 3 plus c. We'll come back to those later. But the motivation behind this, and to get the depressed cubic, is so that all the powers of y are in this case odd. Now that the quadratic term has been eliminated, we are now going to assume the nature of the solution. So step number 2 is going to make a new substitution. We're going to assume that this depressed cubic equation has a solution of the form y equals u plus v, a linear combination of two things. So our cubic equation, our depressed cubic equation, if it has the solution u plus v, by substituting that into the equation and making a few algebraic manipulations, we can get this equation to look like u cubed plus v cubed plus 3uv plus p times u plus v plus q equals 0. Now, in order to solve or satisfy this equation, we're going to assume or let u cubed plus v cubed be equal to negative q. Therefore, those two terms would cancel them out in the equation. And that would then imply that 3uv plus p times u plus v is equal to 0. But since we're assuming that our solution u plus v is not equal to 0, that would make 3uv plus p equal to 0. And a little bit of manipulation there would show that u times v is equal to negative p over 3. Cubing both sides of that equation, u cubed v cubed is equal to negative p over 3 quantity cubed. So now we have a system of equations. I'm going to solve one of those equations for u cubed. Then I'm going to substitute it into the other equation, and therefore have one equation with one variable, v. Now, doing a little algebraic manipulation on this equation, we can turn this into v to the 6th power plus q times v to the 3rd minus p cubed over 27 equals 0. This is something we would call a tri-quadratic equation. And by making a third substitution here, we'll let v cubed equal t, so that v to the 6th would be t squared. Substituting this into this equation, we get t squared plus qt minus p cubed over 27 equals 0. Now that's a quadratic equation which we can use the quadratic formula to solve for. And we get negative q plus or minus the square root of q squared minus 4 multiplied by negative p over 3 cubed, all over 2. And we can clean that up a little bit nicer by absorbing the 2 into the square root and simplifying the term. So we get negative q over 2 plus or minus the square root of q over 2 quantity squared plus p over 3 quantity cubed. Now, we recall the value of t was really v cubed. So by taking the cube root, we can find the values for v1 and v2, the two solutions that we're looking for. Negative q over 2 plus or minus the square root of q over 2 quantity squared plus p over 3 quantity cubed, all underneath the cube root value there. And we can separate those out into two separate values. v1 could be the positive of the values and the negative with the plus or minus inside the cube root. Now the Greek letter delta is going to be used here to signify q over 2 squared plus p over 3 cubed. And this would be the discriminant of the cubic equation. Just like the quadratic equation has a discriminant, this one too has a discriminant. If this discriminant is positive, greater than 0, then that indicates the cubic equation will have one real solution and two complex solutions. If the discriminant value is 0 exactly, then we will have three real solutions, two of which will be the same, a duplicate. And then if the discriminant is negative, then we will have three distinct real solutions, and that's what we have in our case here. Now, although there are three distinct solutions, we're actually only going for the primary or the first solution. So here's the thing. U cubed and V cubed, when added together, equals negative Q, and U times V equals negative P over 3. These two equations are symmetric with respect to U and V. What does that mean? That means if I were to interchange U and V in the equations, it would not make a difference whatsoever. The equations would be exactly the same. So therefore, that's going to allow us to write our solution in the following way. If y is equal to u plus v, then we can let u be the, let's call it the negative cube root, the one with the negative symbol inside it, and we can let v equal the positive cube root solution, the one with the plus sign, or positive sign in the middle. So when we construct our solution for y and write y is equal to u plus v, then we can use these two cube roots as our primary solution. So this is y equals u plus v, which is our first solution. Y1 is equal to u1 plus v1, and that's the, we'll call it the negative cube root plus the positive cube root. Now if we consider that's case 1, there are some other combinations we could put together for u and v. Namely, what if we put together two positive cube roots or two negative cube roots? Playing around with the plus or minus inside the cube root. So those cases, call them case 2 and 3. If we examine how they play out, we realize they do not represent legitimate solutions to our equation, and the only genuine solution to our equation is this first one, u1 plus v1, which is the sum of a negative cube root and the positive cube root. Now, to access the other two cube roots, because there are always three cube roots to find in a cubic equation, we would need to employ the use of complex numbers. And for now, we're going to leave that alone. We don't really need to access the other two cube roots here. We just want the primary cube root. We just want one solution, the first real solution. So x, reminding you that x is equal to y minus a over 3. Our y was equal to u1 plus v1. Then that would make x1, our solution that we're looking for, equal to u1 plus v1 minus a over 3. So the primary solution to our cubic equation is going to be x is equal to the cube root of negative q over 2 minus the square root of delta, which we know was q over 2 quantity squared plus p over 3 quantity cubed, is added to the cube root, which has the positive value inside, minus a over 3. Now, the next thing we're going to do is going to apply this idea to the cubic equation we looked at earlier. 8x cubed minus 4x squared minus 4x plus 1 equals 0. Now to start, I'm going to divide out by 8 throughout the entire equation, turn it into a monic polynomial. And that's going to give us x cubed minus 1/2 x squared minus 1/2 x plus 1/8 equals 0. Now recall that p can be calculated by finding b minus a squared over 3. But really, after finding that number, we want p over 3. And that number is going to work out to be negative 7 over 36. Next, in order to calculate the value of q, we would need to calculate the values for a cubed over 9, a cubed over 27, ab over 3, and c. then taking that q value and dividing it by 2, we would get 7 over 432. We also note that a over 3 is equal to negative 1/6. Now, y cubed plus py plus q equals 0 is our depressed cubic. Its solution was y equals u plus v, and the solution to our original equation is x equals y minus a over 3. Substituting the values that we just calculated, we're going to find that the value of our equation, when we plug it into this grand equation here for the cubic, and I'm just going to write it out here in full form before we actually substitute the numbers in, just to appreciate what this formula looks like in its entirety. Now, substituting in the values we found for q over 2 and p over 3, as well as a over 3, we're going to get the cube root of negative 7 over 432 minus 7i cube root of square root of 3 over 144 plus the cube root of negative 7 over 432 plus 7i radical 3 over 144 plus 1/6. As a decimal value, we can approximate this as 0.9009688, 679, etc. And yes, although we didn't say that we were going to get into complex numbers, we can only express this answer with complex numbers, the complex number I. And this is our primary solution to this cubic equation. But what's so special about this cubic equation is where it came from. You see, I started this search to find the sine of pi over 7 in an exact form, and it led me to finding the exact value for the cosine of pi over 7. And here's how. Much in the same way that I found the sine of pi over 5 in our last video, I'm going to use a similar approach to find the sine of pi over 7 in exact form. And breaking up 7 theta into 4 theta plus 3 theta in a similar fashion as I did in the last video, and using a few substitutions, some trigonometric substitutions, I will be able to generate a cubic equation. Here's how. I'm using a few double angle formulas for sine. In fact, I'm applying the double angle formula twice. And once I do that, I can then notice that each side of the equation could be divided out by a value of sine of theta. And the reason that we're allowed to divide out by a value of sine of theta on both sides is because sine of theta is not equal to 0 in this case. So here's how I'm going to do that. You see, sine theta not being equal to 0 allows us to divide by it. So, dividing out by both sides by sine of theta, we get 4 cosine theta cosine 2 theta equals 3 minus 4 sine squared theta. And now employing a double angle formula for cosine and a Pythagorean identity for sine squared, everything in this equation can be written in terms of cosine theta. And you see, theta here really represents pi over 7. So by finding cosine of theta, we're really finding the cosine of pi over 7. And as we reformulate this equation, we begin to see the cubic equation that we solved emerge. You see, if we let cosine of theta equal x, then our cubic equation, 8x cubed minus 4x squared minus 4x plus 1 equals 0, appears. And again, because the cosine theta is really the cosine of pi over 7, our solution to the the cubic equation is given in exact form, but it can only be done by expressing it with the complex number I. This is actually one of the first ways that people discovered complex numbers, was finding this number in the solution to cubic equations. That's pretty amazing. A sine of something cubic. That was pretty cool, right? Hey, thanks for watching. I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos. Stay tuned.